We start with reactants, reactive intermediates A and C. The interconversion in this case has a comparatively very high activation energy, so the rate is comparatively slow. Practically, the reactants are non-equilibrating. So, this does not follow the Curtin-Hammett principle. A goes through a transition state, and this lower activation energy means that A is more rapidly transformed into B. C also more rapidly goes through a transition state to become D. The key aspect of this generic reaction profile fits the reaction of these two stereoisomers of tropane. One is less stable, similar to A in the generic case, whilst the other is more stable, like C. The two isomers, practically speaking, do not interconvert. It's as if they were isolated from each other. When exposed to sulfuric acid, the amines are comparatively rapidly protonated to become ammonium ions. The minor product comes from the less stable, least abundant isomer, whilst the major product originates with the more stable, more abundant isomer. Reactants, reactive intermediates A and C, have a comparatively low mutual activation energy and thus interconvert rapidly as they equilibrate. A can become another transition state with a significantly greater activation energy than the AC activation energy. This irreversibly continues to product B. C also has an alternate transition state, again with an activation energy significantly greater than the AC activation energy. This irreversibly leads to product D. The conversion of A to B and C to D are both notably slower than the rate of AC interconversion. This is underpinned by their activation energies, and in this theoretical example, A, B, and C, D activation energies are the same. The consequence of this is that the ratio of the concentration of A to the concentration of C remains the same throughout the reaction's duration. The ratio of reactants, reactive intermediates, A's concentration to C's concentration is the same as the product's ratios, B's concentration to D's concentration. Thus, ultimately, the relative energies of the reactants control the ratio of products. The outcome is very similar to the non-equilibrating scenario, but for very different reasons. Here, reactants, reactive intermediates A and C, equilibrate with each other due to their small mutual activation energies, providing fast reactions in between themselves. A has yet another possible transition state that provides the largest activation and energy of the system, which results in product B. C's other transition state gives a lower activation energy than A to B, but much larger than A to C, as the molecule is transformed into product D. Thus, the rate of formation of B from A is the slowest of all the reactions in this system, whilst the formation of D from C is still much slower than A to C's equilibration, but not as slow as A's conversion to B. C is of lower energy than A, whilst A to B's conversion has a greater activation energy than C's conversion to D. Because A and C can readily equilibrate, the ratio of A's concentration to C's concentration remains constant throughout the reaction. These factors make D become the dominant product. Both the relative activation energies of A to B and C to D and the relative energies of A and C can be invoked to rationalize this outcome. However, while not apparent in this scenario, it is the relative activation energies that determine the control of the reaction. An example that has the key features of this generic scenario is the oxidation of 4-methyl N-methylpiperidine into the corresponding amine oxide. One of the two stereoisomers of this N-methylpiperidine is less stable, like A, and the other is more stable, like C. They equilibrate comparatively rapidly due to the small activation energy between them. Upon exposure to hydrogen peroxide, the less stable stereoisomer has the slowest conversion into its corresponding amine oxide that constitutes the minor product. The other stereoisomer's oxidation rate is significantly slower than the A to C equilibration, but faster than the other N-methylpiperidine's oxidation. So, this second N-methylpiperidine gives the major amine oxide product. In this scenario, reactants or reactive intermediates A and C rapidly equilibrate due to their low activation energies with each other. However, this is relative to the accompanying reactions. A can also go through a transition state to become B, with a smaller activation energy than that of C's transformation into D. So, A's reaction to become B is much slower than the interconversion of A to C, but faster than C's conversion into D, and that is the slowest reaction of all. C is of lower energy than A. Whilst here, the activation energy of A's transformation into B is less than C's transformation into D. A and C's ratio of concentration remains constant for the duration of the reaction. Ultimately, the major product is B. It's clear that here these relative concentrations of A and C would have the opposite effect of the D product dominating. Thus, the only rationalization of this result must be due to the lower activation energy providing the major product. A reaction that is exemplary of the key features of this generic reaction energy profile involves the carbon-13 methylation of tropane. One tropane is less stable, like A, whilst the other is more stable, like C. In protonation, the tropanes are non-equilibrating, but this is relative to the reaction they're undergoing and the energy provided to the system. And here, with methylation, the tropanes are equilibrating due to their relatively fast interconversion. Carbon-13 methyl iodide is reacted with the tropanes. The less stable tropane reacts more slowly than the equilibration of the tropanes, but faster than the other tropane's methylation, for the less stable tropane to generate the major methylated product. The more stable tropane is the slowest to be converted into the minor methylated product. In extreme cases, the amount of the less stable reactive intermediate may be so little that it is undetectable, yet it can still become almost the exclusive product.